Okay, we're going to move on to our next talk, and Paul is going to explain us a few things about stuff they have achieved with Replicant.
All right, so greetings everyone. I'm Paul Solkowski, and today I'll be talking a bit about what I've accomplished at the Replicant project and what we're going to do next. So there is my email if you want to send me an email about anything, but remember that we have forums and mailing lists and other public means of communication that enable other people to learn about what you're asking. So please only contact me privately if it's a private matter. Right, so what is Replicant? Well, on our website you can read that sentence. So Replicant is a fully free Android distribution running on several devices. So that's a free software operating system that is putting the emphasis on freedom and privacy and security. So how did it start? Well, from the very beginning it was designed to be some pragmatic way of quickly achieving software freedom on mobile devices. And back when it started, it was in 2010. Well, the situation on mobile devices was the following. We had the OpenMoko FreeRunners, that's this black device. That was really good. I'll talk a bit about it a bit later. It was a really interesting device, and at the same time, Google started the HTC Dream, which is one of the first Android phones, and it got the attention of many developers. So many people were working on that, and some people, mainly from LibrePlanet Italia, thought, hey, let's see if we can run fully free software on that device. Let's see what are the non-free parts that are still needed, and let's try to get rid of them or replace them. So that's how the idea of creating a fully free version of Android came up. So now, since the very beginning, Replicant meant to be an ethical project in the sense that it respects the user's freedom. And it's also, it means mostly that, first of all, we don't distribute non-free software, and we don't recommend the use of non-free software, because we believe that first, distributing non-free software along with the system is taking the decision instead of the user to use non-free software, and we think that's unacceptable for any project or entity. And we also don't want to recommend the use of non-free software because it's the very ground ideas behind Replicant are the ideas of free software. So we do not want to recommend non-free software. And obviously we want something that has some sort of use. We want it to be, to do something, right? Not just to be some theoretical system that you can probably build but not really use. We want something that serves a purpose that you can use as a phone in that case. And we also care a bit about privacy and security, so we try, when possible, to make it better on that regard. So the technical grounds for Replicants are the following. It first started with, as a derivative of AOSP, which is the Android open source project, which is roughly the free version of Android that Google releases when they feel like it, because sometimes they don't. If you remember Android version 3, they didn't release the source code, and we had to wait for version 4. So that's what we use as a base at the very beginning. But if you know about it a bit, you'll see that AOSP only supports a few devices, mostly the Nexus devices from Google. And that's why we decided to switch to CyanogenMod, which is another community Android version that supports really a whole lot of more devices, really a whole range of different manufacturers. So it's more interesting for us because it gives us more devices to choose from when we want to add support to Replicant for those. So I talked a lot about making a fully free system, but what does it mean technically? Well, the main thing that we have to do is to get rid of the non-free software, obviously. So we either just remove it, and in which case the functionality that depends on that piece of software just doesn't work, or we try to replace it. And those non-free bits of software are either executables, so usually daemons that run in the background, or libraries, essentially hardware abstraction libraries. So those are kind of drivers in user space. And obviously we have firmwares, little bits of code that run on chips, that's not on the main CPU, that's on other chips that are aside the CPU. And obviously we also want to get rid of any malicious feature on our system, because we're based off CyanogenMod, but there is some nasty stuff inside CyanogenMod that we don't really want to have in Replicant, especially tracking of the users and stuff like that. CyanogenMod reports to Google Analytics when you use it, and we don't really want that. We have no reason to tell Google that you're using Replicant, so we just get rid of it, obviously. And that's the core work that is being done on Replicant. And obviously there are also some side tasks that are less important, but that we still have to do. And that's mostly, a non-important part is, for instance, branding and look and feel. So we change the background so that you know it's Replicant. Yay. And we also do maintenance and security updates, obviously, like any decent operating system. But one not that trivial part is to adapt the system for the lack of non-free components, because mostly the Android code we get expects that non-free software is in place. It expects, for instance, that we have 3D drivers, but we don't, because 3D drivers on those devices are non-free. So we get rid of them, but the rest of the system expects to be able to use them. So we have to find all sorts of tricks to get it to still be usable and to still work. So that's a real challenge. And it's the same with firmwares, because firmwares are usually required by kernel drivers. They load the firmware and then they start discussing with the chip. When the firmware is loaded, the chip is running something, and so they can discuss. But when the firmware is not there, because we didn't ship it, obviously, because it's non-free and we don't want to recommend using a non-free program, well, the driver very often doesn't handle that very well. So it might retry to load the firmware in a loop infinitely. Some drivers do that. So we have to correct it, else the CPU explodes, and it's a nightmare. So we have to look at those things and adapt and add proper code that says, hey, when the non-free firmware is not there, well, just give up and don't try endlessly to make contact with the chip. It's not going to work. Right. So as I said, we want to have something that works. So that's why we need as many features as we can that work on Replicant. And that's when we start doing reverse engineering, because we can't just say, oh, this is non-free, let's reject it and not use it, because that doesn't work. If you do that, you basically cannot boot the system. You cannot do anything with it. So that's when we start looking at what is the non-free piece doing, and can we do it with free software instead? So that's the whole work that is behind Replicant. And that's reverse engineering. It's a big piece of work. So the non-free parts are really on a variety of different domains. You've got some on graphics, on audio, camera, sensors. So that's the radio interface library. That's what talks with the modem, the hardware component that is in charge of discussing with the telephony network, the mobile telephony network. So we have non-free program for all those things, and even more, like hardware video decoding. There is non-free software for that too. So we have to understand how it works. And how do we do that? Well, we can ask the manufacturers, the companies that actually produce the chips. And when we do, we usually get that kind of response, which is chip maker is not in the position to provide details about the formula that we addressed with the OEM, so the phone manufacturer team. So we're screwed, basically, very often. So we had to really think hard and find ways to still understand what it does. And there are many, many interesting techniques to do that. So we can start by looking at logs and tracing the execution. We can look at strings on the binary. We can decompile it, look at all that, read the assembly. But we can also trace the kernel driver, because thankfully the kernel driver is usually free software. So since a non-free component is using the kernel driver to communicate with the hardware, we can intercept the communication and try to decode it at this point. Or we can perhaps modify it and see how the non-free program response. So that's the sort of thing we do to understand what's going on and to eventually write free software that does the same thing. And sometimes it takes a bit of knowledge in math, especially if you're dealing with sensors, where you have some raw data that's coming and you've got calibration values, maybe 3, 4, 5 different values, and you have to figure out a mathematical formula that takes all these things and put them together to have some result that has a physical meaning in the case of sensors. So if you're working with a magnetic field sensor, that's going to be the case. You're going to have to figure out that formula. And obviously it's very frustrating because very often it fails because it's just too hard. And you need some background on how these things work. So at first it's very frustrating, but eventually we succeed at doing something, right? So eventually we do write some of these free software replacements. And we do that for the things that I listed, but not for every task, because some of them are just very hard, especially graphics acceleration and 3D. That's something that has never been worked on by Replicant developers because it's just very hard and you need people who are into that field and would know what they're doing. So there are some separate projects that do that for some of the devices that we're interested in. So especially there is Freed.mp4, which is reverse engineering project that aims to write drivers for Arduino GPUs, and it's actually very well advanced. Rob Clark is working on that, and really now it's usable and you can do a lot of wonderful things with it. There is also Lima that is being worked on by Luc Verhagen, which is in the graphics dev room just over at the other end of the campus. So that's a lot of very nice stuff that we don't do ourselves and let others do. And obviously firmwares are very hard to write as well because they're not executed on the main CPU. Instead, they're working on the separate chips. So usually they have their own instruction sets and they have all sorts of hardware specificities that are just very hard to figure out. So we just leave that out. And the modem system, so the piece that talks with the mobile telephony network, it's running its own operating system that is all non-free, and we don't even try to understand how it works because it's so complex. And thankfully there is a project that is called Osmocom BB, which does the heavy lifting for that for a few old modems, which are Calypso modems that you can find on the OpenMoko that I mentioned a bit earlier. So that's great. All these projects are doing these things and we're not doing it ourselves. But we still do stuff, right? So over the past, I think, 3 years, that's the stuff I have written. So for the radio interface library, I wrote Samsung Real and Leap Samsung IPC. Thankfully, on Leap Samsung IPC, we had external contributions. So that's 30,000 lines that work on 9 devices. Then you have camera stuff, so that's 5 to 10,000 lines for devices, audio, sensors, you get the idea. We wrote a good amount of free software to get those devices to work. And thankfully, sometimes other communities are interested in lending a hand and helping me do the work. So we had the SHR and FSO community for Leap Samsung IPC. So if you're not familiar with those, SHR is an operating system that was initially written for the OpenMoko. It's a GNU and Linux mobile operating system. So it was interesting for them because they wanted to get it to run on Samsung devices, so they contributed to Leap Samsung IPC, so that was great. And we also have other community Android versions, such as CyanogenMod, also Omni, and Team Haxon, which is a specialized team of people working on Samsung hardware. So all of those were interested on the camera and audio parts because we wrote that for Samsung devices. And that work usually is shared between CyanogenMod and Replicant. So when I write something for Replicant and CyanogenMod people are interested in it, they usually take it and goes the other way around and we share patches and stuff, so it's pretty great. And for them, if they're not that interested in having a fully free software stack, it's also a great technical advantage. Well, I'll mention that a bit further. Yeah. Right, so that's a rough timeline of what happened. It all started in December 2010 with the HTC Dream. Then Google was kind enough to send us a Nexus 1 when it came out, so we added support for that as well. That was on Replicant 2.2. I joined in April 2011, worked on the SDK a bit. That's the software development kit. Then we went on to work on Leap Samsung IPC, so that's basically the library that talks to the modem on, it was the Nexus S at the time, but it's the same protocol on most Samsung devices. So it started with the Nexus S, but then we extended it for other devices. So then we worked on Samsung Real, added support for the Galaxy S, then the GTA04, which I will mention a bit further. It's a very interesting device for many reasons. We started adding support for it in September 2012, but we kind of gave up. I kind of gave up midway, and you can see that back in June 2014, I started to work on it again. So I'll just detail that in a bit. And along the way, we added support for new versions of Android. So we went from 2.2 to 2.3 to 4.0 to 4.2, each time adding new devices. So at this point, we have a good number, I think 10 or 11 or 12 different devices supported. And each time we want to add support for a new device, it's a big challenge because devices are essentially very different one from the other. But thankfully, we find similarities, especially so on the radio interface layer, as I said, we have Samsung Real, which communicates with the Android framework, and that part is common to all devices. It's written in a generic way, and actually last summer I've completed a total rewrite of it from scratch because the old code was not that good. So I rewrote that, and it's really generic, and it works well on all 11 or 12 devices. So Leap Samsung IPC, that's the device-specific part that implements the different kernel interfaces to communicate with the hardware. So that's what we need. So that's a big part of the work that was done on Replicant. And then you can see that there are different generations and families of devices. So those are using the same chips. On the Nexus S and Galaxy S, you've got a Samsung S5 PC 110, that's the code of the SoC. On those, we had to work a bit on the camera to get preview working without graphics acceleration. That was a bit of a challenge. Sensors, also we had to figure out how do the accelerometers work. That's what you need so that your screen rotates when you rotate your device. Also, the magnetic field sensor was it was kind of challenging on both devices. That's what you need to get Compass. If you're lost and if you have a Compass application, it's going to use the magnetic field sensor coupled with the accelerometer to figure out the position of the north, basically. And that's how you find your way. So that's kind of important, right? And on the Galaxy S2, Galaxy Note, that's basically the same device. The Galaxy Note has a bigger screen, but it's really basically the same hardware. There was a big problem with audio because they're using a non-conventional chip, which is the Yamaha MC1 and 2. And people at CyanogenMod were calling it Yamahel because there was a whole lot of non-free libraries that did not integrate well with the standard Android environment. So it was terrible for them, and at some point I just looked at it and wrote a free implementation for audio. So that was a big challenge as well. It was kind of hard, but doable. And the same thing was going on with the camera. The camera needed a non-free module, so I replaced that as well. And on the Galaxy S3 and Note 2, so that's a newer generation, There was the same problem with the camera, which needed a non-free blob. So then again, I replaced it. It was a different interface. So I kind of reused the same code, but mostly changed it. So it was a bit of that. And the back camera was very interesting, the S5C73M3, because it has a very unusual interleaved format. Because if you look at the propaganda, the marketing stuff for the Galaxy S3, you'll see that on that device you can actually record a video and take photos at the same time. So that implies that the data that we get is both a preview frame that is used for recording and a very high quality frame on demand. So I kind of had to figure this out, and it was not so easy. All right, so that's the stuff that was accomplished mostly. And where are we today? Well, currently there is one developer working on it. That's me on spare time. I'm kind of busy, so it's not moving forward very fast. We have very few external contributions. Mostly the list I gave earlier is where it stops. That's just 3-4 different groups that helped because they don't really anymore. Our latest version is based on CyanogenMod version 10.1, which is Android 4.2. And we support up to 12 different devices, which are mostly Samsung Galaxy and Nexus devices. So why those devices? Because they're the easiest ones to liberate, basically, because they don't require so many blobs, so we can do it, and because Nexus devices were good at the very beginning because it was easy to install another version of Android on them. Nowadays, it's kind of normal that you can reflash your device with another operating system, but back in 2012, it was really hard to find devices that would allow that. So that's why Nexus devices and Samsung devices, just because the chips they're using, the Exynos chips, are actually not so bad for freedom. And I mean, I'm used to working on those, so yeah. And the whole thing is funded thanks to donations. I'm not paid for the work I do. And devices are expensive. When you have to buy 12 different devices, yeah, it's a lot of money. So that's why we ask for donations, and it really helps. And also to fund trips like this time to FOSDEM, so that I can even talk to you right now. That's funded thanks to donations, so that's really great, and thanks everybody for your support, really. So that's what I've been doing. I say we because I'm the only active developer, but some other persons are involved in the decision-making process. Especially, we're working a lot with the Free Software Foundation that handles donations for us. So we kind of discuss the directions for the project, and past developer Gnutu, Donny Karikli from his real name, who started the project, is still around. He's not contributing technically very much, but we discuss a lot about what should we do, what we should do, and what will be our next steps for the future. So that's where we are now. And well, if you take a step back and look at those, that's the devices we support. All right, cool. But all of those have what we call bad modem isolation. It means that on those devices, the modem, which is always connected to the mobile telephony network and running non-free software, well, this piece of hardware has access to the rest of the device to a certain extent. We know that on the Nexus S and Galaxy S, it can read and write the RAM, and that's very bad. If you have some sensitive data, or if you're doing encryption or whatever, the fact that non-free software that can be controlled remotely has access to your RAM mostly compromises your device. So that's really terrible for privacy and security. And the HTC Dream and Nexus one, well, those are Qualcomm platforms where the modem and the main processor are on the main chip. So we can have very strong suspicions that the modem can access basically everything. And we know, for instance, that the modem system is stored on the same memory as the operating system. So if the modem can load the system from that storage, it can also load your data and can probably certainly also modify your data. So that's an incredible risk for security. So those are very bad devices. Well, what about the others? Well, we cannot tell for sure whether the modem isolation is good or bad. We just don't have any clue that it's bad, but it doesn't mean it's good. It just means we don't know, right? Because the only way we can find out about those things are mostly unreliable. I mean, we cannot just open the device and look at the board. It's incredibly complex. You've got multi-layer circuit boards. We can't just look. It's too hard. And when we know that it's bad for sure, it's because we have it in, for instance, the kernel source code. It's very clear that the random access memory is shared between the modem and the CPU. So then we can say, yeah, okay, we know it's bad for sure. So all those devices may be good, but we don't really know. And then you've got that problem with bootloaders. Bootloaders are basically the equivalent of the BIOS on x86 platforms. So that's kind of the first piece of software that's executed at boot. It's not exactly, because there is something before the bootloader, which is called the boot ROM, and that is read-only on the SoC chip itself. So that you cannot modify, and it's always going to be there on every single SoC. But the bootloader, that's the next stage. It's before the kernel. Well, that piece, you can reinstall, you can modify, in theory. But now what happens is that on most modern devices like those, on most modern platforms, the chip makers decided that the bootloader would have a numeric signature. So just kind of like a GPG signature, where you have a private key that you use to sign the binary, and you have a public key that you use to verify the signature. Well, in that case, the boot ROM inside the SoC has the public key, and it uses that public key to check whether the signature is correct or not. And if it's not, it refuses to boot. So what does it mean? Well, it means that if you want to replace the bootloader on those, you need to have the private key to sign the bootloader so that it will allow it to boot. And obviously we don't, because the private keys are, well, private, so we don't have access to them. And what does it mean in the end? Well, it just means that we cannot have free bootloaders on all these devices. So all the time we've spent trying to liberate these devices, well, in the end, it cannot be, it's limited. We cannot do any better than that. We cannot free it anymore. We cannot have a free bootloader. So that's a big issue. So what do we do now? Well, there are basically two different directions. The first one is to say, well, that's the way it is. We'll just keep adding support for more devices. We'll just try to catch up with Samsung, who makes a new revision of their Galaxy S line every 6 months or whatever. We'll try to, work and have those supported. Great. So to do that, obviously, we need the latest Android versions, because the new phones are not running Android 4.2 anymore. They're running on the new version. So we have to keep up. And that's a lot of work to keep up with the new devices, the new versions. And it doesn't really bring anything for freedom, because that's what we're mostly concerned about. We want software freedom, right? And on those, we know we're not going to have non-free bootloaders. And we will try to avoid the devices that have bad modem isolation, so mostly the Qualcomm platforms and others that we know are bad. We're going to try to avoid those. Well, of course, that's a good idea, because to some extent, it's a good idea, because if those devices are going to exist, they might as well run a fully free system. Even if they cannot have a free bootloader, it's already something, right? So it's great. But we have, I have very limited time. So what else can we do? Well, there is a second idea, which is to focus on a smaller number of devices, but devices that are essentially better, that do allow to have free bootloaders, and that were not proven to have bad modem isolation. That's why it says allegedly good modem isolation. And that's how we take freedom to the next step, right? That's really, that's moving forward. So obviously, since I have very little time, I decided to go with that solution. And I'll be talking a bit in the second part of that presentation about what exactly I've been doing lately with that in mind. And by the way, we also often get people asking me or the community, but why do you keep working on Android, right? Everybody knows Android's crap, and why do you still work on it? Why not Tizen or Firefox OS or Ubuntu Phone or whatever? Well, there are basically two reasons. The first one is that, or even three reasons. The first one is that Android is quite mature, right? We've got all the features around that are already there. We don't need to write any of the interface. We don't need to do any of that. We just have to take it and replace the non-free drivers, which are also on Tizen and Firefox OS, because obviously those projects, they're a new free operating system, but really what they replaced is just the common stuff, what was already free in Android. So the framework, the applications, that's nice, but that's not really what we need. What we need is free hardware support, right? So that's one reason. Another reason is that Android supports really a crazy amount of devices. I don't know if you can even count the number of Android devices out there. It's incredible. If you look at Tizen or Firefox OS, I know that Tizen released the Samsung Z, something like that, a few weeks ago, which is the only official Tizen device. So, well, that's one device. That's not much interest. And if we're going to have to port Tizen to another device, it's going to be a lot of additional work. And we don't really have time to do that, right? We want to write hardware support. That's what's important. And Firefox OS, that's basically the same story. You've got some officially supported devices, more and more of those, but they're Qualcomm devices, so to us, they're not interesting at all. And, well, it's kind of wasting our time. And, yeah, that's why we still go with Android. So really quickly, the Open Moco Freerunner. So that was the first historical example of a good device. It had free PCB design and isolated modem, no loaded non-free firmwares, but obviously still non-free firmwares running inside the chips that were pre-installed. You can say it's firmwares, you can say it's equivalent to circuitry. You decide. Right. So it had free bootloader, free system and all, but it's kind of old. It's only 400 megahertz, 128 megabytes of RAM. That's low end and that's kind of slow. And eventually the company that made that phone retired and the community also retired. There are still a few systems like Qtmoco and I think SHR is rebooting in a way, but that's mostly the past. So that's when a company called Golden Delicious in 2011-2012 decided to introduce a motherboard replacement for that device, and that's the GTA-04. It's just that motherboard that you insert back in the GTA-02 case, and it's new hardware. You have an OMAP 3, which is reasonably efficient. By today's standards, it looks maybe now a bit slow, but it's still better than the Open Moco. So I've got that stuff, many cool hardware features, and most importantly, it has a free bootloader. It doesn't, the chip doesn't check the signatures, so you can actually build your own bootloader and install it. We have supposedly good modem isolation because we have mostly the PCB design, so we can check that to an extent, even though we cannot know that the schematics match the actual board. I mean, it's still something, it's not perfect, right? And a friendly manufacturer, Debian supported, and the chips are well documented for the protocols they use, so that's great. So obviously I was interested in that device very early, right? In mid-2012 on Replicant 2.3, started getting involved in that, but there was really a lot of trouble with the modem. No, sorry, the kernel, right? We had no power management support, a lot of issues with suspend and resume. So it was not really good. And you also, when working on Android, you also have the problem of getting the Android parts of the kernel working with the rest of the kernel, because the kernel that existed for the GTA-04 was a regular kernel Linux kernel at the time. It didn't have any of the Android pieces, so I tried to add that and miserably failed because it was technically hard. I think I was in high school, I didn't really know what I was doing, so it just failed. And there was, at the time, nobody else to pick up the work, so it just stayed there for a year or so. And thankfully, Golden Delicious, the company that produces the phone, came up with a Linux 3.12 kernel that has decent support, that, on which it was easy to merge the Android features, and on which PM is kind of working. There are still issues, but it's better. So at this point, I started working on Replicant support. So that's why you can, on the timeline I showed previously, you could see that the GTA 04 support was back. And that's where it is now. So we have two versions, one made by the manufacturer, Golden Delicious, where they use a single partition approach, which allows them to have multi-boot, multiple operating systems in parallel. They also support other form factors because they also make a tablet with a bigger screen and stuff. They have work in progress radio interface library, so to make calls and stuff. They have work in progress sensors, and they ship the non-free Wi-Fi firmware, something we don't want to do and that we won't ever do. On the other hand, on the official Replicant version, we have a typical Android partition scheme where you have 3-4 partitions that are separate, and this allows for having encryption because Android is the Android system is expecting that sort of partition layout, and so that's how encryption is implemented. So on the upstream Replicant version, you have encryption, and we also have recovery, which is a nice interface to install the system, whatever. So what about the future? So there is a community called Open Phoenix, which is just a community really about the GTA 04 and other devices that are alike, like the Neo 900, which is an upcoming motherboard replacement for the N900 that was originally made by Nokia. So the plans for the future regarding Replicant is for me to add real support, sensors, Bluetooth, all the stuff that's missing basically on the official Replicant version, so that you can use all those things. That's important, obviously. We want to have a fully operational kernel, so no more PM issues. That would be cool. And have multiple devices support, so also the tablet versions of that hardware supported, and all with a single image. So that would be interesting, because on Android, you usually make one image per device. And that's a waste, because when the devices are really close, you could have some runtime changes and optimizations going on. So that's what I'll try to do. So there you have some links to learn more about these projects, and you're welcome to pre-order the next revision of the GTA 04 or your Neo 100. Those are really interesting stuff, really interesting things. Right, so mostly what I wanted to talk to you about today, and I'll probably have to be fast because I'm kind of running out of time, that's the LG Optimus Black. So over the last few months, I've written a series of blog articles called A Hacker's Journey Freeing a Phone from the Ground Up. So it's all about this device, the LG Optimus Black, which was released by LG back in 2011. It has an OMAP 3 platform, just like the GTA 04. And the technical documentation leaked online about it. So that on that file, you get basically all the electrical wiring of the device. You get many relevant information about it. So it's really, really great. It's something really nice. We have U-boot and Xloader, so those are bootloaders. So source code was released by LG because I think those are GPL licensed software. So they released the source code, the modified source code, so that's really great. And what's really interesting about it also is that it's an OMAP GP device because the OMAP, so that's the SoC made by Texas Instruments, you have one high security HS version which does check the signatures, as I mentioned earlier, and you have the GP which does not. And usually on mainstream devices you get the HS version. And on this one, we were very lucky to find that it's a GP device. That's devmem something, that's how you find out what it is. 03 means GP, and I think if we had 0A, it would have meant HS. So we were lucky. So no signature checks, free bootloaders are possible. Well, that's great, but how do we run code on the device? How do we replace the bootloader, right? Because that's what we want. We want a free bootloader, we want to replace it. Well, let's first think about how it boots. To find out where it's going to load the bootloader from, there are this series of resistors which indicates what's the boot priority, right? Because you've got different options, and obviously the bootron has to decide where to look for the bootloader first, and then second, and so on. So that schematics is extracted from the technical documentation that leaked. So you see a few resistors. Some have a little box around them, which means that they may or may not be there. So what I did basically was to open the device. You get the board like that out of it. Just get a very good lens, and you just try to know, is that resistor there or not? So eventually I came up with this schematics, which is the reality, what's actually on the device. And so you see that when you're wired to 1.8 volts, that's a logical 1. When you're wired to ground, that's a logical 0. So from that, you get the sysboot thing. And when you look at the OMAP documentation, it says, well, if sysboot 5 equals 0, and if you have sysboot bits 0 to 4 that equal this, it means that first off, you have the MMC, and second, you have the USB. So the MMC is internal storage. And that's great, but if I want to develop my own bootloader, if I install it to the memory and it fails, I'm not going to be able to write a new version on it, because it just won't boot. So I need to have USB first, right? And if you look at the documentation, you can see that when sysboot 5 equals 1, it's the opposite. It's USB first and then MMC1. So what I needed to do was to change sysboot 5. And as you can see, it's the only one that has 2 resistors. So I figured that if you remove one of those, you're going to get either 0 or 1. Currently it's 0, I want it to be 1. Well, what do? I remove the resistor from, which is down there, connected to ground. Then I get, a logical 1 on sysboot 5, and USB boot first. So it means removing a resistor on a very tiny board like that. It's possible. I've done it 3 times, I think. I succeeded every time, and I'm not very good at soldering, so if you just have good equipment, it's possible to do it. So that's just one very tiny resistor to remove. That's the schematics, that's the actual board. So you can see it's kind of, yeah, very tiny. And when you do that, you connect USB and you see this, which is the bootron asking for code. So that's great. Now we can load our code, but now what? We're still blind. Sure, our code loads, but we don't see it running, right? It's not going to initialize the LCD. It's really complex to do that. So how do we get some output? Well, that's when you need serial output. So that's UART. And that's something you need to see what's going on. So where do you get UART? Well, you've got some connectors on this side of the board. And if you can see, that's as big as that. So you've got to solder two very tiny wires on those pads. It's incredibly hard. I've succeeded twice, I think. But every time when putting the board back on the case, the wire would break or something, and so it never worked out. And eventually, I found out that you also have UART on some switch that is accessible from the board. So I just find out about where physically the connectors are on the chip, and just soldered a very tiny wire there. And eventually it worked. After some time, I was able to finally load my code, and it said free software for free society, which is nice. And so, yeah, it worked. So now it was time to begin the real work, right? And so I made some very big contact pads so that it would be reliable. And in the end, device looks like this. It's the same one, where you have serial connectors that are easy to use. So it was time to actually start the work. There was a version of Xloader by LG that I used at first, but it turned out that Xloader is kind of deprecated. So I made it work, had a problem with I2C, but I'm not going to detail it. It's on my blog, read it if you're interested. It was fun, you know, it was hard and fun, and I learned a lot, blah, blah, blah. Eventually, I started adding upstream support for it, using the U-boot SPL instead of Xloader. You know what it is if you're familiar with U-boot. That's the first stage bootloader. So that's what I did, using the reference code from LG, because I can't just invent what it's supposed to do. I just read and adapt in a clean upstream way. And already got a few patches accepted, some that are generic to the OMAP or stuff like that, because if you want to send patches specific to the board, you first have to commit the board support. And it's not ready yet, so it's going to be one very big series of patches that I will submit when the basic stuff is ready. So at this point, there is muxing, external SD card boot, stuff like that. USB support I got running, I think last week, with fast boot, so that's the usual Android thing. So with that, you will be able to reflash the device easily, to load the kernel from USB, stuff like that. And the kernel I'm using is Clockwork Mode Recovery. That's the usual recovery thing. It's pretty great because you've got the interface and everything on an init RAMFS, so you don't really have to have a full system aside. So yeah, useful. For the future, I'd like to have LCD keys detection to decide what device to boot from, and proper kernel boot because there are some issues with that. Getting serial out of the USB connector would be very nice too. It's possible on the hardware. You have switches where you can direct the serial to the USB connector. So that would allow most people to get serial without having to solder on the switch like I did. So that's something nice to have. And obviously I'm going to add replicant support for it. The challenges will be to add real support and sensors. I'm going obviously to document all of what I did on the replicant wiki, which I didn't do yet because I was very busy, and have maybe upstream kernel support at some point. That would be nice, why not? Not so many phones run upstream Linux, so that's an occasion to do it, why not? And it's not all that great though, because some features will still be missing with free software, especially GPS. It's a chip that picks an unknown protocol that I didn't figure out. The DSP, so that's for, in that case, it's used for video decoding. That's not going to work without non-free software, and Wi-Fi and Bluetooth, the usual. So just very quickly, I'm also going to focus on Arduino tablets. I just started. Those are great because you can also run U-boot and free bootloaders on them. There was a great community called Linux Sancti. I think I'm not the first person to talk about it today. So Arduino's, the company is not very supportive, but the community is very great. You've got some high quality drivers and code written for it, so that's really cool. I'm going obviously to add replicant support for that, and since there are so many cheap Chinese tablets that add support for that, that use that platform, I'm going to try to add support for all of them at the same time. So with a single image that can adapt at runtime to each tablet. So that will be challenging, but I have a pretty clear idea on how I'll do it. So those I don't have time to discuss, but it's interesting stuff. So yeah, I already have a handful of devices, I think 5 or 6. So I'll be adding support for them over, you know, like the next month. I'll try. And so yeah, there are challenges because every hardware is a bit different. So we have to have kernel drivers for each tablet and user space modules. I don't really have time to detail that so much, but you can also add support for your own device. Then a few other things I would like to do soon. That's adding support for the Kindle Fire, because it's also a GP device, but it's on the map4, it's a bit more recent. It's also a very interesting device. There is already a free bootloader on it, so that's great. There is maybe more devices, more interesting devices to discover. Also, I'd like to update the Replicant wiki so that it would have stuff for device evaluation. So how do you find out whether your device is good or not? That would be interesting. Have a bit of documentation about how each device is flawed regarding privacy and security, and also modem isolation. Make a list of which devices have signed and non-free bootloaders, all that stuff, and how to get UARTs and stuff. So that's something to do. Right, so if you want to learn more about Replicant, website, blog, and wiki, that's the places we usually use to communicate. To mostly announce stuff and provide content. To communicate, we have our forums, mailing list, IRC channel, and you're welcome to get in touch with me, with the community, to maybe get involved and do stuff. So that's all. Thank you for your time and attention. Do you have time for questions?
Not really.
Not really? Okay, so if you have questions, you can just catch me on the way out or whatever.